Okay, this video here is part 2 for the video on functions and graphs. So here it says graphs of functions, and first of all we're going to talk about the vertical line test. A graph is that of a function if no vertical line passes through more than one point on its graph. So determine which of the following are functions. On number 1, I can draw several vertical lines that go through more than one point, and so this is not a function. In fact, to see why this is true, if you look at these 2 points, and you can do this with any of the 3 lines that I drew, notice the points there are 0, 2, and 0, negative 2, and these 2 points have the same x value with different y values, and so that is the situation when you have something that's not a function. You can't have the same input with 2 different outputs. Alright, so let's look at number 2. If you draw vertical lines, no matter where you draw a vertical line, you can't go through more than one point. So that one is a function. You might want to go ahead and try number 3. So notice you're okay here, but what about there? In fact, there's a few places where you're going to go through more than one point. So if anywhere on the graph you can go through more than one point, it's not a function. All right, let's move on. So here we're going to graph a couple of functions. So when we run into a new function, normally what we do is we will make a table of values. And here I think I would start with x equals 0. Excuse me, I could let x be anything I want. If I let x be 0, that'd be f of 0 equals the square root of 0 plus 1. Well, that's the square root of 1, which is 1. And let's go ahead and try 1. F of 1 would be the square root of 1 plus 1. And that's going to be the square root of 2. And if you check it on your calculator, that's about 1.4. Now, I really don't particularly care to get these decimal values if I can avoid it. In fact, what kinds of numbers do we like to take the square root of? That would be perfect squares. So notice if I put in negative 1, the square root of negative 1 plus 1, that's the square root of 0. Well, what number squared gives you 0? That would be 0. So negative 1, 0 is a nice point. Notice if I plugged in 2, I would get the square root of 2 plus 1. That's square root of 3. And again, 3 is not a perfect square, so let's try a different choice. How about if x is 3? The square root of 3 plus 1 would be the square root of 4, and you would get 2. So let's go ahead and plot these points on the graph. And in fact, the graph would look like this. Notice there's nothing left of that point on the left, negative 1, 0. In fact, if you plug in a negative 2, for example, or any other number to the left of that point, any x value, you would be taking the square root of a negative number, which is not a real number. And so for now, well, actually, that's all we could do at this point. When we do graphing, it's got to be real numbers. You may recall that there's such a thing as imaginary numbers, but when we're graphing, everything's real. I always say keep it real. All right, so let's look at number 5. So we'll do the same thing. And again, let's try 0. F of 0 would be 0 cubed minus 2, which is negative 2. If you were to plug in 1, well, we could do this in our head. 1 cubed is 1, and 1 minus 2 is negative 1. How about 2? Well, I'll go ahead and, let's see. 2 cubed is 8. 2 times 2 times 2. Minus 2, you do get 6. Let's try plotting those points. So they look like this, and in fact, if you plugged in 3, you would actually get a pretty good sized number. You'll see that the graph looks like that as you go to the right. So what if we choose an x value on the other side, like x equals negative 1. Well, negative 1 cubed, negative 1 times negative 1 times negative 1, that would be negative 1. Minus 2, you're going to get negative 3. So that would be that point. Let's try one more. How about g of negative 2? I'll just go ahead and plug this one in. You get negative 2 cubed minus 2. Well, negative 2, if you multiply 3 negative 2's, you get negative 8. Minus 2, you're going to get negative 10. And so we get the point negative 2, negative 10. We're a little bit off the grid here. And so you can see your graph's going to look something like that. In fact, you may know your, if you actually know your square root graph and your cubed graph, normally the cubed graph has this point at the origin. So really this is just the graph of x cubed, but it's down 2. Later on we'll be talking about shifts, and that's the type of thing that we'll be discussing. So I just want to point out something here. Certainly you should all be able to use ordered pairs to get graphs like this, but we also want you to know how to use your calculator to be able to put functions like this into your calculator. So I want to make sure you know how to use your y equals button. In fact, if you hit y equals and then you put in these functions, you should be able to graph. And we'll actually do this in class. I'll make sure you see it at least a couple times. And you can also talk to other students. And most of the time, there are many that have experience putting functions in their calculators. And then I would encourage you to use Zoom Standard. All of these are at the top of your calculator. And that's basically a window that's got 10 tick marks to the right, to the left, up and down. So that's a nice window for graphing, and you might play around with some of the other ones on that Zoom screen. You should also be able to use the table feature, which will give you the table we just got plus a lot more, and you just use second graph to get that. So for now, that should be enough, but we're going to continue to learn how to use the graphing calculator. All right, let's move on. So on number 6, it says use the given graphs to find each of the following function values. So on A we have f of 0, and notice this function is a line. And so basically notice 0 is an input value, or an x value. And so what we really want to do here is look where x is 0, and I need to find the point on the graph that has an x value of 0. Well, that would be that point there. It's just right below. So that's the point 0, negative 1. So 0 corresponds to negative 1 on this graph. And so f of 0 is equal to negative 1. And you can do the same thing with b. So x is negative 1 right here. And so this would be the point that has an x value of negative 1. That's the point negative 1, negative 3. And so f of negative 1 is equal to negative 3. Negative 3 is the value that corresponds to an x value or an input value of negative 1. Now that's one way you can do these problems. I think there's a better way. And so I'm going to go up to the upper right hand corner here, and I want to show you something. So I'm going to draw this graph, and my question to you is, when you look at a graph, what is it that you really care most about as you're reading the graph? Is it the x values or is it the y values? Well, let's answer that question. So in this case, I could label, and often we do this, the x-axis will be your time, or we sometimes call that the independent variable, which always goes on the x-axis. And then I could say, for example, here that on the y-axis we're dealing with home values, or average or median home values. So what this graph is saying is, in 2015, the average or median price of a home was around a little above 200,000 in Dallas, we'll say. So I'm going to go ahead and put a point on this graph. So this would be the point 2016 comma 200,000, which again tells me in 2016 the average price was 200,000. Actually, I probably should have made that like maybe we should have said 200. Oops, wrong one there. 220,000. That's not right. So what is the number that I really care about when I read this graph? It's not the year 2016 that I really care about. It's what was the average value of a home there. And in fact, you can see the graph is rising, so my y values are getting bigger. So I like to think of my y values, which is what I care about, as the height of the graph. So here, the y value is just this height. Or here, the y value is just this height. And so when I read a graph, this is the way that I do it. So let's go back to f of 0. So basically, when x is 0, what's the height of the graph? Well, it's down 1. So f of 0 is negative 1. When x is negative 1, what's the height of the graph? This is b. Well, notice we're down 3. So f of negative 1 is equal to negative 3. What about f of 2? Well, when x is 2, what's the height of the graph? Well, isn't this line, that point is up 3, isn't it? And so f of 2 is 3. So why don't you go ahead and do D and E. All right, so when x is 2, what's the height of the graph? Well, we're down 1, so g of 2 is negative 1. G of 4, isn't that also the same? We're down 1, and so g of 4 is also negative 1. And that's fine, they both have the same output. How about, why don't you find g of 5? So you could see that g of 5, well, here at 5, the height is 2. That's this height here. And so g of 5 is 2. And so that's how you can read a graph, and that's an important part of, it's an important skill when we're doing college algebra. You should be able to read a graph this way. And we'll be doing a lot of other types of reading of graphs. All right, let's move on. So here we're going to focus on domain and range of a function. The definition is the implicit or implied domain of a function includes all values of x for which the output is a real number. So notice with linear functions, the domain is all real numbers, quadratic the same. For rational functions, it's all real numbers excluding any values of x that cause the denominator to equal 0. Because we know when we're dealing with fractions, that's what rational expressions or functions look like. They have fractions in them. We can't have 0 in the denominator or we're undefined. So for right now, you can see that right here. Really, it's just with rational functions that are going to have a restricted domain. All of our other functions are going to have a domain of all real numbers. Now this symbol is a symbol that we use for, it's kind of a shortcut for writing all real numbers, but sometimes you'll see it this way. This is called set notation, and really this capital R here is just a shortcut notation for that. We read this, the set x, such that x is a real number. So that's using set notation. The one we're going to use, the one we'll focus on, is what's called interval notation. And that would be, in this case, negative infinity to infinity. So if you're not familiar with interval notation, I would encourage you to watch my video on interval notation. Remember, all the videos are in my math lab in our course. All right, so, and then I wanted to point out, really, when we say all real numbers, those are all the numbers that we can represent on the number line. And so basically, we would shade the whole number line. All right, so let's go ahead and do these problems. Find the domain of each function. Write your answer using interval notation. Well, really, the only problems that will not have a domain of all real numbers would be 4 and 2, because those are the ones that are rational functions. Remember, I said all the others are going to have a domain of all real numbers, at least up to this point. We'll run into some later on where that's not the case. But let's go ahead and look at this a little more closely. If you look at number 1, let's plug in a couple of values. F of 0 would be negative 2 times 0 plus 3. Well, that's going to be 3. So the idea is, no matter what I plug in, will I get an answer that's a real number? Or is there any value that I can't plug in? Well, all this in this function, all we're doing is multiplying our input by negative 2 and adding 3. Let's do one more. F of 1 would equal negative 2 times 1 plus 3, and you're going to get 1 there. So really, no matter what you plug in, can't you multiply any number by negative 2 and add 3, and you're just going to get another real number? Don't really have any issues with this one, and so our domain is all real numbers. Now, look at number 2. That's not going to be true for this problem. Certainly, you can plug in most values. Like here, if I plug in 0, I have 4 times 0 over 0 minus 5. Well, that's 0 over negative 5, and 0 divided by any number other than 0 is 0. Now, the question is, can I plug in any number into this function? Well, we said that our denominator can't be 0, so really x can't be 5 here, because if I plugged in 5, in the denominator I'd have 5 minus 5, which is 0, and I'd be undefined. 4 times 5 is 20, 20 over 0, it's undefined. So this is my only value that I can't plug into this function because it causes the denominator to be 0. So how do we write our answer here? Well, we go from left to right when we write interval notation. So if you look at the number line on the left side, we're at negative infinity, or I call it negative infinity land. And eventually we get to 5, and we can't include 5, so we'll put a parenthesis around that, and then union that with 5 to infinity. So this is basically how we write all real numbers except 5. Because I used a parenthesis next to 5, we were not including 5 in the set. If I had used a square bracket, that would be wrong because we'd be including 5. We'll get to some like that later, where we have square bracket on domain or range. So number 3, again, there's really no number that you can't plug into a quadratic equation. I could plug anything in for x here, and my answer is going to be a real number. So our domain is going to be all real numbers. Again, number 4 is a rational function, so we've got to make sure our denominator is not 0. Now, it's not as obvious as number 2, so what you can always do is set your denominator equal to 0 and solve for x to find out what values cause the denominator to equal 0. Well, you're going to have to factor here to solve this equation, and that's one of the skills we assume you already have in this course. I'll put up a video where you use quadratic or factor to solve quadratic equations. There's actually other ways we could do it, like quadratic formula, but the easiest way would be to factor. So here in this problem, notice my coefficient of x would be a 1. Whoops. And when we factor it, we should get two binomials. Notice x times x is what gives you that x squared if you were foiling this or multiplying it out. So we need two numbers that multiply to negative 12 and add up to 1. So I usually make a little table. And let's see, our factors of 12 would be 1 times 12, or 2 times 6, or 3 times 4. Those are all our possibilities. And we need these numbers to multiply to negative 12, so one of them must be negative. The other thing is the two numbers need to add to 1, so we want to make sure the bigger numbers are positive. So let's make the smaller one negative. And so in each case when we add these numbers we get a positive. The one that gives us positive 1 is negative 3 plus 4. And so those are the numbers we're going to use here. So we have x minus 3 times x plus 4. And if you multiplied those two out, you could check yourself and see that we do get what we started with. The next step is to set each of your factors equal to 0. Because if we multiply two numbers and we get 0, one of the numbers must be 0. Either x minus 3 is 0 or x plus 4 is 0. And so when you solve for x, you get 3 and negative 4. Now remember, those are the values that cause x squared plus x minus 12 to equal 0. Those are the values that would cause our denominator to equal 0 or make us undefined. And so those are our restricted values. X can't be 3 or negative 4. So going from left to right, we would go from, well actually I'm going to go ahead and draw a picture here. Notice if you drew a number line, basically it's the whole number line except negative 4 and 3. So it'd be negative infinity to negative 4. And then we would do a union symbol. And then everything between negative 4 and 3. And then another union symbol, and then 3 to infinity. So it's a little bit long to write this out, but that's how you would write that in interval notation. 5 and 6, we know the domain's going to be all real numbers. We're going to get into graphing in a minute. You may recall on number 5, the graph actually looks like that. And we'll find domain of graphs in just a minute, but the domain's going to be all real numbers. And the same thing for h. If you actually graph that one, the graph looks something like this. And again, that's also going to have a domain of all real numbers. So let's look at some graphs to see how we can visually determine the domain and range of a graph. Alright, so it says determine the domain and range of each function. I think I'm actually going to stop here and I'll make one more video because this one's getting a little bit long. Maybe not. We'll just make it a little bit long. Number 7. So if we're finding domain and range here, I want to remind you that remember the domain was a set of all the x values and the range was a set of all the y values of the points that are on our function. So if we want to find the domain, we're going to go from the leftmost to the rightmost point because we're moving along the x-axis, and we'll look at x values because domain always deals with x values. So let's go ahead and do that. So if you look here, hold on just a second. This graph goes forever left. There is no leftmost point. And so we say it goes to negative infinity on the left. And isn't that true on the right? There is no rightmost point. It goes forever to the right. In fact, if you look at all the x values of the points on this graph, you hit everything. Notice if you're at negative 2, I should say that's the point where x is 0. That's the point where x is negative 1. And all these points in between have x values between 0 and negative 1. And as we keep going to the left, that's where x is negative 2, negative 3, negative 4, negative 5, and we're hitting all the points in between. So there is no point as we move to the left or to the right. You can see x is 2, x is 3, x is 4, and since this thing goes forever right, there's not going to be any biggest x value, and we're going to hit everything in between. And so let me go ahead and erase this here. Our domain is going to be all real numbers. What about the range? Well, when you're finding range, you're going to go from, so we're moving along the y-axis now because we want to look at y values. You go from the lowest to the highest point and you look at y values. So again, in this graph, There is no lowest point. Doesn't this graph keep going down? So notice right here, the y value of this point is, what are we down, 5? And as this graph goes down again, more and more, there's not going to be any lowest point, and your y values are going to continue to get smaller. So here the y value is -4, here it's -2, here it's here it was -3, and here it's -2. But as you go to the left, the y values are just going to get smaller and smaller. There's no lowest point, so it goes to infinity. And notice as you go up the graph, so here y is 0, here y is 1, and as you keep going up, your y values will just keep getting bigger. And again, these points in between, you're hitting all of those y values, in this case between -2 and -1. So we're hitting every y value as well. So our range is all real numbers as well. Let's look at B now. So in this case, we do have a leftmost and a rightmost point. The leftmost point is right there, and the x value there is -2. What about the rightmost point? Well, there is a rightmost point, and the x value there is 3. And so if you look at the x values on this graph, at all these points, they're going to go from -2 to 3. Now -2, this point is on the graph, so we start at -2, so we'll have a square bracket. So going left to right, at our leftmost point, the x value is -2. At our rightmost point, the x value is 3. And so our domain is -2 to 3. And again, what that's really saying is on this graph, all the x values are between -2 and 3. Now let me use a different color here. So for the range, we're going to go from the lowest point, that would be this point here, and now we're looking at y values. The y value there is -3. And we do have a highest point. Wouldn't that be this point right here? And at that point, the y value is 6. And so at your lowest point, the y value is -3. And at your highest point, the y value is 6. Notice I'm using square brackets because these points are on the graph, and so we have to include their x values. And basically what we're saying is if you look at all these points on this graph, their y values are going to be between -3 and 6. All right, let's move on to C. In fact, I encourage you to try C and D and then watch the video. You can always stop the video and then turn it back on. So on C, for domain, there is no left or rightmost point. You can see that at the two ends. And we're hitting every point in between. And so this one has a domain of all real numbers. The range is a little strange on this one though. Aren't all the y values 1? Every point on this graph has a y value of 1. So we're going to write this differently. We don't need interval notation. We would just write it like that. That's the set with just 1 in it because there's only one value in the domain. On D, the domain is all real numbers. Notice there is no left or rightmost point, and we're hitting every point in between. If you look at all the points on this graph, x could be anything. Like when x is -2, you're right here at this point. X is -4, you're right here. This point, every point on this graph, we're going to hit every x value. The domain is all real numbers. What about the range? Well, if you look, notice you could look on either end, but this graph goes down on both ends. There is no lowest y value, there are no lowest point. And so we start at -infinity, but we do have a highest point, and that would be right here, and the y value there is 2. And so the range goes from negative infinity to 2. So what we're saying is there is no smallest y value if you look at all the points on this graph, but your highest y value is going to be 2 at your highest point on the graph. All right, and so I'm sorry about that. That was a longer video than I normally like to make, but we got it all done. And that's it.